for our next presentation, and the next presentation will be given by Sravya, and she will be presenting her work on agent goal management using goal operations. And Sravya, please go ahead.
Hi, can you hear me?
Yes, we can, and we can see your screen as well.
Okay, thank you. So, hi everyone, welcome to my talk on decision making or agent goal management and agent goal management using goal operations. This research is supported by NSF and ONR grants. So let's get started. So here is how the next few slides are organized. First, I'm going to introduce you to what we think about when we say intelligent autonomous agents. Then I'll just present you the algorithm that we have developed for agent selecting its own goal operations. And then I'll introduce you to the problem domains in which we have implemented our work. And finally present you the empirical results that we got and conclude my talk. So intelligent autonomous agents. So when we use this word, we assume that that there are certain capabilities that the agent must have in order to be considered intelligent. And a few of the capabilities are perception, thinking, action, and communication. Meaning the agent should have the ability to perceive the world around it, and then it should have the ability to think, process those percepts, and generate its own thoughts or goals based on those percepts. And it should also have the capability to act to achieve its goals in the real world using its control mechanisms. And then it should have the ability to communicate, meaning it should be able to explain its thoughts or thought processes to other agents in the real world, or even to a human as well. So while developing such intelligent autonomous agents, there are several issues that we face or the agent faces. Two main issues are unexpected events, meaning since the real world is continuously changing, the agents need to cope up with several changes in the real world. Meaning, let's say if I have an agent and I ask it to go switch on a light, and in the meantime a human comes in the door and switches on the light, our agent should be able to observe the change and should be able to change its goal or plan according to the change in the world. And partial observability, this is one issue that we face as humans as well, meaning it is limited in its observability, and it should be able to incorporate changes in the world as it progresses its work in the real world domain. And some of the examples of such agents are self-driving cars or humanoid robots like Simon or Sophia or several others. So with this in mind, in general, when we talk about intelligent autonomous agents, they do not usually have one goal, but they have multiple goals that they should act on, and the agents must have the capability to manage all of their goals on their own without human intervention. So so for which we have developed certain goal operations that in general we humans do as well. So let's take a look at what those operations are. The first one is goal selection, meaning when we give a bunch of goals to the agent must not wait for a human to tell it what goal to do next. Instead, it should be able to figure out the next goal or the current goal that it is going to pursue on its own. And that is one goal operation. And there is goal change operation, meaning let's say if I have if I have a robot with me and I just give it $20 and ask it to go get a cake from a store, and it goes and it sees that the cakes are on sale and it could get a bigger cake for the same price, then it should be able to kind of change its goals to a similar one, to grab the opportunity, right? So that is what we mean by goal change. And there is also one other goal operation called goal formulation, meaning when there meaning the agent coming up with its own goals when there are when there is minimum to no help to use. Essentially it should think on its own when some unexpected event occurs, and be able to handle it on its own. There are several other goal operations that we have presented in the past as well, and you can find those in several of our references pointed out below. But in this paper we will be focusing on just these 3 goal operations. So I've pointed out the 3 goal operations so far, and more often when the agent is working in the real world, one operation doesn't occur at one time, meaning there are multiple situations when the goal operations co-occur or occur at the same time. For example, let's say if the agent is working on its selected goal in the real world, then let's say a fire erupts in the room beside it. Should it still continue working on its goal, or should it go deal with the fire? I mean, it solely depends on the situation, right? Meaning if the fire is because of a matchstick or a small lighter, it should not run around with a fire extinguisher to put out the fire, right? So yeah, it's completely based on the situation, and the agent must be smart enough to have the understanding of the situation and make smart decisions um, according to the changes in the real world. So yeah, to handle such situations, we have developed an algorithm. This is an extension to our conference paper, which will be presented on Thursday, 18th at Advances in Cognitive System Conference. And yeah, so what we did was, so we looked at the situation at 3 different scenarios, meaning whenever an anomaly occurs, the agent needs to have or at least strive to collect the information on how the anomaly affects the agent's goals, how the anomaly affects the agent's health, and how often does the anomaly repeat. And we have developed certain functions to calculate these and also qualitatively represent the values. And then in addition to that, the agent must also have the knowledge on how important the goal that it is currently working on to either its mission or to itself. So for which we have used work of Dr. Roger Schank, and we have categorized the goals into crisis goals, preservation goals, and achievement goals. Crisis meaning the goals that the agent would generate in a crisis event, or a hazardous event. Preservation meaning the agent working on a goals to either preserve its health or resources or energy, or all those kinds of goals. And achievement goals are the general goals that the agent works towards in its real work, in its mission, meaning just the goals that it tries to achieve are the goals that are essentially provided by a human, could be classified as achievement goals. And in addition, the agent must also have the capability to track its resources. So we have developed an abstract algorithm, and if the agent would be able to estimate would be able to achieve 85% of of its goals, then we say that the resources are sufficient, and if not, we classify the resources as not sufficient. And based on all these qualitative readings that we get from these different parameters, we have put forth some generic rules, and if the values from these qualitative parameters match those generic rules, the agent would be able to make a decision in the real world. So we again, I would love to go into the details of the algorithm just maybe after the talk. And so we have implemented our algorithm in 2 different domains. The first one is construction domain, and the second is the marine survey domain. The construction domain is a very simple domain. It's an extension to the Bloxwell domain, in which the goals are to simply construct towers of different heights, and the agent would have blocks and motor, and the agent, if it uses motor, it could construct sturdy towers. If not, the tower would be wobbly. And we give different reward for these 2 different reward types. And the anomalies in this domain occur in the form of an arsonist or a thief. Arsonist would light fires onto the towers, and thief would steal the resources, meaning the blocks or the motor, from the agent. So if these occur very randomly, the agent must deal with the arsonist or thief. And again, this is just a simulated domain. And so on the second domain, we've worked on a much more realistic domain. And this is a real world problem. There is a Grace Reef National Marine Sanctuary off the coast of Georgia Savannah, where marine scientists catch these fish and tag them with acoustic transmitters and leave them back in the ocean. Here we have several underwater autonomous agents that need to survey the entire region and collect the data regarding the ocean environment as well as the fishes. So these are the actual coordinates of Grace Reef National Marine Sanctuary area, and the orange area is research only area, and the rest of the area is accessible by public as well. So before working or deploying our algorithm onto the real robot, we used a Moose simulator to test our algorithms. So this is again the same area. We have divided the area into 25 equal regions, and we assumed the fish to be static at this point, and we have 1,000 fish in total. The red small dots everywhere are the fish, and the red cylindrical object here is our agent. We call it Grace, and the gray area around it is the sensor, meaning whenever the fish falls within the sensor radius of the agent, it would be able to detect it. And in this domain there are several anomalies. We'll talk about them in a minute. And usually the mission range is 1 to 2 months, and the agent surfaces once every 4 hours. So there is very minimal communication, and it can only communicate when it's on the surface, and when a surface vessel is nearby. If it could not find a surface vessel nearby, it needs to use satellite communication, which is very costly. And so let's take a look at the goals in the domain again. As I said, so the goals in the domain are to gather several measurements about the environment and discover the fish, and also identify hotspots, meaning the regions where highest density of fish live underwater. And as per the problems in this domain, there are remora attacks, meaning there are 12-inch fish, kind of sucker fishes, which latch onto our robots and eat the paint layer off of the robot. So in order to get rid of those remora, the agent needs to glide backwards, and there are blowout situations, meaning flow, which would throw the agent into open waters. We do not want that happening. And there are obstacles, meaning coral reefs and everything, that hinder the motion of the agent. And there are also shark attacks. Again, at this point of time, although it only happened once, we do not know how to deal with the shark attacks yet. So as per the empirical results in the construction domain, we assume that there are 100 blocks, 100 regular blocks, and there are 100 motor blocks, and we have 30 different problem sets. We have repeated the problem with 2 different seed values, meaning randomizing when the arsonist and thief acts. And again, as I mentioned, the anomalies in this domain are arsonist and thief, and the performance metric that we have measured is the percentage of goals achieved. I'm sorry for the typo there. And for comparison, we have generated 4 agents. One is baseline agent, meaning it would only work towards achieving the goal, and it would completely ignore all the anomalies that it encounters. And there is random agent, meaning the agent that chooses these goal operations in random. There is smart agent, which uses the algorithm that we have developed. And there is ideal agent, meaning the agent that works in a perfect world where there are no anomalies. So
Sravya, your 5-minute warning.
So here are our graphs obtained in the construction domain. The red is the ideal agent, green is our smart agent, purple is our random agent, blue is our baseline agent. So everything is as expected here, although our smart agent takes a little bit of time. It would eventually reach the performance of the ideal agent. And similarly, in the marine survey domain, we assume that there are 1,000 fish tags, and again, we assume that they're static and they do not move. And Grace begins surveying at 100 different initial locations, and we have so essentially we have 100 trials for each experiment, and we run the experiment with 3 different seed values, meaning randomizing when these anomalies occur. And once again, to measure the performance, we use the same agents. So in this domain, as you can see, the baseline is right at the bottom. The purple, the random agent, it might make some stupid decisions because, or stupid decisions in terms of choosing goal operations. So it kind of flatlines at 70% of the goals. Our green, which is smart agent, eventually, although it takes some time, it reaches the performance of the ideal agent. And yeah. So in conclusion, so all of our work is openly available at the following link, and we agree that much of our work is still in preliminary stages, but the results that we have are surely exciting and assuring, and we believe that combining the simulation studies paired with the field trials will definitely advance the field of intelligent autonomous agents and also goal-driven autonomy. Thank you. I can stop for any questions.
Thanks, Sravya, for your presentation. And I have a question from Pat. So do you really need 3 types of goals, or could you encode them as a single type with different temporal constraints? The later approach might cover other varieties as well.
Any questions?
Yeah, Sravya. So
that was a question.
Yeah, this was a question. So do you really need 3 types of goals?
In your talk, you referred to 3 types of goals: achievement, preservation, and crisis, I think. And it seemed to me that you might be able to get that effect not by having different goal types, but having some types of some temporal constraints on your goal to say when they need to be achieved They maybe they're already achieved. You want to keep them achieved. They aren't yet achieved. There's an urgency. So do you really need 3 types, or might you get by with a single type with temporal annotations?
So yeah, it is something that I have not thought about until now. But by temporal constraints, do you mean like having time limit on each goal, when to achieve each goal? And
it's more than that. It would, I mean, for example, an achievement goal is something that's not true now, but you want it to be true in the future. If it's crisis, it might be something you want it to happen soon. A preservation or a maintenance goal is something that's already true that you want to keep true.
Oh,
right? Those sound to me like temporal constraints.
Okay. Yeah, I mean, yeah. So that is, yeah.
It's not high urgency.
Hi, Pat. I lost you.
I said it's not a high urgency problem.
yeah. I mean, there could be situations when crisis is not always the priority. Meaning, let's say again, to reiterate on my example, the fire goal. I mean, if it kind of assumes the fire to be a crisis goal in general, we need to also incorporate the intensity of the fire, and it might make things a little bit more complicated. So yeah.
Oh,
it is something to think.
I didn't mean to say that there weren't other factors that would determine how important something was to the agent. My point was that you might be able to get away with not having different types of goals, but rather a single type of goal that be my temporal annotations. That this is I'm sure there are other.
I'll definitely give a thought on your suggestion then.
Well, it's a classic distinction in the literature, so you're in good company. I'm just saying that maybe there's a way beyond.
Yeah, sure. Thank you.
Thanks, Sravya. And